Hi, my name is Kyle Bear, soil scientist and president of Soiltest Farm Consultants in Moses Lake, Washington. Today, I would like to show you how, step by step, I read and interpret a soil analysis report. Our laboratory produces reports in various formats, and today I will give you 3 examples of such formats. The first thing that I'll note is where the sample comes from, in this case, Ephrata, Washington. The first thing that I'll look at after that is the pH. pH is measured on a 1-to-1 soil to water slurry. What that means is we'll take 20 grams of soil, mix it with 20 milliliters of deionized water, and measure the pH. In this case, it's 6.6. Soils that are below a pH of 7 are considered acidic, while soils that are greater than 7 are considered alkaline. On that same 1-to-1 slurry, we measure electrical conductivity. Electrical conductivity is the measure of salts in the soil solution. The higher the salts, the better able the soil slurry is to conduct electricity. The units are given as millimos per centimeter. This number is useful, however, in order to make an interpretation on the value, we must first determine what the estimated saturated paste electrical conductivity is. What we do is we take our 1-to-1 electrical conductivity that we measure, multiply it by a factor to obtain a value of 0.34 in this example. Crops vary in their tolerance to salt, and so in order to make a comparison, we must first know what the estimated saturated paste EC is, but we also must know the tolerance level for a given crop. Beans, for example, will show decline in production when the electrical conductivity is greater than 1. Below the electrical conductivity is effervescence. Simply put, this is a fizz test. We'll take the sample, add a small amount of water to it, and dribble on hydrochloric acid. We observe the amount of fizz that is produced by the sample. We list it as either high, medium, low, or in this case, none. The amount of effervescence is directly related to the amount of free lime in the soil. The higher the free lime, the higher the effervescence. This box on the right is used to show nitrogen at various depths in the soil. First of all, we'll measure nitrogen in 3 forms. Ammonium nitrogen, we'll measure it as nitrate nitrogen, and then include a contribution from organic matter breakdown and mineralization. Let me show you how this works. In the laboratory, we'll report ammonium in milligrams per kilogram. This is the same thing as parts per million, in our case 1.9. In order to make more sense of these numbers, we'll use a factor to determine pounds per acre. The factor is dependent on where the sample came from. Because the soils near Ephrata are mostly sandy, we'll use a factor of 4.0 to determine the pounds per acre. In our case, we've taken 1.9 parts per million of ammonium, multiplied it by a factor of 4, and determined that the pounds per acre of ammonium is 8. This factor is dependent on the region. As I said, Ephrata tends to have soils that are high in sand, therefore they have a higher bulk density, and we use a factor of 4. Whereas samples on the west side of Washington and Oregon states might have more organic matter and a lower bulk density. In those cases, a factor of 3.2 is more appropriate. This factor further is dependent on the depth of the sample. In our case, we're using a 0 to 12 inch sample. Had we taken only a 6-inch sample, we would have used a factor of 2 up here to multiply our parts per million by to obtain pounds per acre. Next, the organic matter is listed. These initials next to the organic matter, WB, stand for Walkley Black, which is the method that we use to determine organic matter. The percentage is listed, and next to it we have a value called ENR, which stands for estimated nitrogen release. Organic matter will break down through the process of mineralization throughout the growing season. This process creates ammonium and nitrate, which are used for plant production. Again, a factor is used to estimate how much nitrogen is going to be available from the breakdown of organic matter. We use two factors generally, one for irrigated ground, one for dry land. This field is an irrigated field, and so we use a factor of 35 to determine our ENR. So percent organic matter times 35 gives us our estimated nitrogen release from this soil. In this box, we list our nitrate, nitrogen, and sulfate sulfur results. This box is expandable based on the number of samples that have depth related to them. For example, if a field is sampled from 0 to 12, 12 to 24, 24 to 36, and so on, those values would then be shown in this box that can expand. In our case, we measured nitrate on the first foot at 2.7 parts per million. Again, this value is multiplied by a factor of 4, and we determine that our pounds per acre of nitrate that's available is 11 pounds. Sulfate sulfur is also listed, and moisture would be listed if it had been requested. In this case, it was not. This 11 from nitrate, the 32 from our estimated nitrogen release of organic matter, and 8 from ammonium are all used to determine our sum of tested N, which in this case is 51 pounds. On the left-hand side of the report, we have the different macro and micronutrients. They are listed by the nutrient, the method used to extract that nutrient, the units that are given, and then finally in the last column is the result. In the top line we have phosphorus, which was extracted by the Olsen method, which is a sodium bicarbonate extraction. The units are again given in parts per million or milligrams per kilogram, and the result is 12. Similarly, we list potassium, which is extracted with ammonium acetate. Boron, zinc, manganese, copper, and iron are all extracted with a DTPA sorbitol extractant. This extractant is a chelate, and the sorbitol is a sugar that's able to extract boron. The chelate is used to extract the zinc, manganese, copper, and iron. Lastly are the basic cations, calcium, magnesium, and sodium. Like the potassium, these are extracted with ammonium acetate. You'll notice that the units here listed are not parts per million. In this case, they are milliequivalents per 100 grams. We do this for convenience when we extract or determine the cation exchange capacity of the soil. Cation exchange capacity is listed in units of milliequivalents per 100 grams. So, in order to determine the percentage that these cations occupy of the cation exchange capacity, we list them in the same units for convenience. If one wanted to determine the percentage of calcium that occupies the cation exchange sites, with the units listed as milliequivalents per 100 grams, they would simply take the result of the calcium divided by the CEC, and they would be able to determine the percentage of calcium that occupies the cation exchange sites. In this case, cation exchange capacity is not measured, but I have an example on a subsequent report. Total bases is also calculated. This value is calculated by adding the calcium, magnesium, and sodium. Also, potassium is added to the basic cations. You will notice that the units that potassium is listed at is parts per million. In order to determine the milliequivalents of potassium in the soil, we divide this value, 133, by 291, and that value, together with the 7.7 from calcium, the 2.3 from magnesium, and the 0.21 from sodium, are added together to give us 10.6 milliequivalents per 100 grams of total bases. Now, all this data is used below to give us a fertilizer recommendation. Now there's a few things that we need to know in order to give a good fertilizer recommendation. First, we need to know what crop we're growing. Second, we need to know what the previous crop was. And we also need to know what the yield goal is going to be for our crop. In this case, we're planning to grow a 160 bushel per acre crop of hard spring wheat, and this is following a grain corn crop. On the left-hand side, we have our results from up above that are listed again. The 51 from the nitrogen comes from this part of the table. The phosphorus right here is the same value as is listed up here. These values are used to determine our fertilizer requirements for this crop. The graph shows us relative amounts of these nutrients. For example, at 51 pounds per acre, our nitrogen requirement is somewhat high for growing a hard spring wheat crop. In this case, we're going to need an additional 450 pounds of nitrogen per acre in order to grow that crop. Now, one thing that you'll notice down here is that phosphorus, potassium, sulfur, boron, zinc, and manganese are all listed in parts per million, where nitrogen is listed in pounds per acre. There are a few reasons for this, but the most important one is that we do not calculate pounds per acre of these other elements because in order to make an interpretation of the data, we have to know parts per million. None of the fertilizer recommendations that were developed by Washington State University, Oregon State University, University of Idaho, that are the basis for our recommendations, use pounds of phosphorus per acre. They all use milligrams per kilogram. There are other reasons, but we won't get into it in this discussion today. In our case, like I said, we need to add 450 pounds per acre of nitrogen. Our phosphorus is also a little bit on the low side, so there's a recommendation for 15 pounds, 75 pounds of K2O, 20 of sulfur, and a pound each of boron and zinc. And these recommendations are based on a growing season. And so the application of nitrogen especially can be made over several applications. It's important to note that these recommendations are really only a starting point. Based on your cropping history, your experience with how well certain crops do in the field, you might feel it necessary to adjust the recommendations up or down based on your experience. Here's an example of a report that comes out of Reardon, Washington, which is dryland country. And really the biggest difference of this report compared to the last one is that we are now listing our nitrate, sulfate, and moisture on not only the topsoil, but sub-increments as well. In this case, we're going from 0 to 6, 6 to 12 inches, 13 to 24 inches, and lastly 25 to 36 inches. Now, as I said before, because we're only taking a 6-inch sample, the factor that we're using to multiply our parts per million to get pounds per acre is half of what it would be when we have an entire 12-inch increment. In this case, 13 to 24 would use a factor that is double what we use up here in this 6-inch increment. Now, all of these nitrate values are calculated in pounds per acre and then added up. And so in this case, our sum of tested N is 128, which includes 69 of nitrate, 56 of estimated nitrogen release, and 3 of ammonium. Another way that this report is different is that we have now listed chloride. Chloride is an extraction that is done with water and is often of interest for wheat growers in arid conditions and in non-irrigated dryland conditions. Again, at the bottom of this report, we have our yield goal. In this case, they're wanting to grow a 50 bushel per acre soft spring wheat crop, and this is following beans. So, again, if we look at the data, we've got 128 pounds of nitrogen, and in this case, we don't need any more application of nitrogen because it's sufficient. We have a small, modest application of boron that's recommended and a 1 pound per acre of zinc recommendation. This final report format is intended to be used on samples that come from more humid, wet climates. You'll notice a few differences about this report. The first is that we include a calcium chloride pH. This pH is measured when a weak salt, calcium chloride, is added to the sample. The result of adding that weak salt is that some of the acidity is drawn out of the reserve acidity in the soil. And the result is that we end up with a pH value that is a half to a whole unit less than the 1:1 pH. Another difference here is that we've measured a buffer pH. In this case, we have measured the SMP buffer. SMP stands for Smith-McLean-Pratt. Basically, the process of this analysis is that we know where the SMP buffer pH is at to begin with. We add sample to it, and after mixing and allowing it to sit, we measure the pH again. In this case, it came back at 5.5. That 5.5 and the 4.6 of the calcium chloride pH are used in a table to determine the lime requirement. On the report, the lime requirement is shown immediately above that in tons per acre. In other words, this lime requirement of 3.6 means that we need to add 3.6 tons of lime per acre in order to raise our soil pH to 6.5. That is the goal of the lime requirement. A few other things that are shown on this report are the cation exchange capacity. And this is a measured value of cation exchange capacity. A lot of labs will sneak around that and try to just add up the cations to get the cation exchange capacity, but in a lot of cases that is not a good method for analysis. We have our total bases, which again is the sum of the calcium, magnesium, sodium, and our potassium after converting it to milliequivalents per 100 grams. This total bases is divided by the cation exchange capacity to give us our percent of base saturation, in this case 10.2%. Lastly, we give a measure, or a calculation rather, of exchangeable sodium percentage. Simply, what we've done here is we've taken our sodium value of 0.12, divided it by the cation exchange capacity, and that gives us a result of 0.5%. When this value gets up near 15%, that's where we are concerned about a condition called dispersion in the soil. When the soils and the clay when the clay particles in the soil are dispersed, they tend to cause poor infiltration, surface sealing, and therefore poor plant growth. So this is a number that we'd like to keep an eye on if we have too high of sodium. Another thing to make mention of, the phosphorus in this sample was measured using the Bray method. In our laboratory, we use 4 different methods to determine phosphorus. On the previous 2 reports, you saw that phosphorus was measured as Olsen phosphorus. That's an extraction that uses sodium bicarbonate to extract phosphorus. In this sample, we use the Bray analysis, which uses hydrochloric acid and ammonium fluoride to extract P. Another extractant for phosphorus we use is Morgan, which uses sodium acetate as an extractant. And lastly, we use a Malick 3 extraction. We decide which extraction to use based on the customer's request, which is driven mostly by the region from which the samples come from. Eastern Washington and Oregon use an Olsen extraction. A Bray extraction is inappropriate for these areas because the phosphorus chemistry in our soils is largely dictated by associations with calcium. And adding a Bray extraction to a high pH soil will dissolve a lot of the calcium-phosphorus complexes and overestimate the availability of phosphorus. Conversely, in low pH situations, Bray is a better extractant for phosphorus. Down here, for convenience, we have done the math for you to determine the percentage of CEC that is occupied by calcium, magnesium, sodium, and potassium. The sodium value is a little bit redundant because we already have it listed right here, but the calcium value is calculated simply as our 1.9 divided by the CEC of 23.8. Same thing for magnesium and potassium. In this sample, the requester asked for a 5-ton grass hay recommendation. In this case, our nitrogen was sufficient at 128 pounds, and so there is a 0 pound per acre recommendation. The phosphorus and the potassium values were both quite low, and so we have a 95 and a 135 pound recommendation for both P2O5 and K2O. Lastly, 2 pounds of boron and zinc are needed in order to grow this 5-ton grass hay crop. I hope this explanation helps you to better understand your soil analysis results. We take a lot of effort to make sure that the results are accurate and timely, and that they can be used in a manner that will be beneficial to you and the crops that you're growing. If you ever have any questions regarding your soil test report, don't hesitate to call us at the office and talk to one of our soil scientists. It's one thing to have all this data, it's another to have the data and include an understanding of how the crop's behaving, what symptoms or deficiency symptoms are showing up, and using all of that information to determine a plan of action for how best to fertilize your crops. We appreciate your business, and we look forward to seeing you in the future. Thank you.